Welcome back. Now, in the previous discussion, we focused on the differential equations and the use of differential equations to define the relationship between the output and the input of a system or a dynamic systems. And we also discussed how to actually determine whether a system is linear or not. And of course, because we have differential equations, and with these differential equations define relationship of the input-output of a system, therefore, this kind of differential equations also tell us basically everything about the behavior or the properties of a system. So in other words, if you know the differential equation, then and you know the input, then you can find the output response by solving the differential equations, rather than going to the actual system experiment. Sometimes it may have the access, sometimes it may not have that access necessarily. But as when the system gets more complex, first order is probably manageable, second order is okay, but if you get to third, fourth, and so on, higher order systems, solving differential equations is no longer a trivial matter. It gets complicated, and it doesn't necessarily always give you an answer. And sometimes people use computers to help you to solve differential equations, but that's a different topic for discussion. In control analysis, we have developed another way of doing it, a much simpler way of solving this problem. Okay, not by solving differential equation, we convert this into a different type of relationship. It will still be an input-output relationship for a system, but it's in a much simpler way. Okay, now to do that, we use this mathematical tool called Laplace transform. Okay, and that is strictly a pure mathematical tool, but we use this quite extensively in control engineering for our purposes. Okay, so for those of you who are familiar with Laplace transforms, and this would look quite easy for you, but if not, if you have not really dealt with Laplace transforms before, then we don't really need to go into the nitty-gritties of the mathematical details. But the principle is like that. It's another way to represent a signal. Say I have a signal, okay, not a system, a signal that is defined by a function, time function, ft. So ft is my time function of a signal. If I multiply that by an exponential function e to the power minus st, and then integrate that from 0 to infinite. Okay, t is integrated, so t will disappear after integration. The only variable that will be left there is this s. So you will end up with something or function of s. Now that fs is another representation of ft. It's not in the time domain, so it's not a time signal, but it is a frequency signal. Okay, that's all. If you don't really get into Laplace transform, this is all you need to know. Ft, every single ft will correspond to a fs. Ft is in time domain, fs is in frequency domain. They are basically representation of the same signal. Okay, so they are the same thing, just expressed in different manners. Okay? That's all we need to know about that. And also we need to know is the Laplace transform of some very typical signals. the signals that we use quite often in control engineering. The first one is called impulse signal. Impulse signal is a signal that has a zero width, okay, but infinite amplitude. But the cross section of the area is 1. Okay, so it happens at an instant. It goes up to infinite, it drops down. All the rest will be 0. Okay, from there to there, there to there, it's all 0. It's that instant, it goes from 0 to infinite. So the width is 0, the height is infinite, but the cross-section area is 1. Okay, so bear in mind that's a very special signal. It's called impulse. We often use delta to represent that impulse signal. The Laplace transform of that signal is 1. Okay, so delta is the impulse in time domain, 1 is the impulse signal in frequency domain. Second signal we need to know is a unit step signal. Unit step signal is when before the time 0, this is time 0 here, okay, t equals to 0. Before time 0, it's all 0. After time 0, it goes to 1. Okay, it's called step because the amplitude is 1, so it's called a unit step. For any time it's greater than 0, signal is 1. And because our discussions are often for time after 1 anyway, so when we say unit step signal, we sometimes just say it's a 1. Okay? The Laplace transform of that signal is 1 over s. So 1 is the signal in time domain. Basically, it's a constant value. Okay, it keeps the constant value. It doesn't change with time. So this x-axis is t. That's varying in time, but value is 1 all the time. Okay, so 1 is the step signal in time domain. 1 over s is a step signal in frequency domain. Okay, just two different representations of the same signal. That's really what the Laplace transform is. We're not changing anything. We just change the mathematical representation of it. Third signal we're going to look at is called unit ramp signal, where signal equals to t. So after t equals to 0. Okay, so this is where t equals to 0. Before that, we have 0. Because there's no point talking about something happened before. So we only deal with things that has happened since you switch on everything. So time 0 is our reference. The Laplace transform of a ramp signal is 1 over s squared. Okay, so in time domain is t, which means the signal goes up with time. In frequency domain, the same signal is 1 over s squared. Okay, just recap. Delta, which is the impulse signal, in time domain is infinite, but in frequency domain is 1. Unit step in time domain is 1. In frequency domain is 1 over s. Ramp signal in time domain is t. In frequency domain is 1 over s squared. Exponential function is all very useful as well. So in time domain, it's e to the power minus at. Okay, t is the time. In frequency domain, is 1 over s plus a. Now this exponential function is e to the minus at. Okay, it's a negative power. And for the Laplace transform of that signal is 1 over s plus a. Okay? If that was e to the positive at, then this would become 1 over s minus a. Basically, that would be a negative signal. So it's fairly obvious there. Now, there are other things as well, which I've listed here, but I'm not going to go through them. But important thing is, remember these pairs. Delta equals correspond to 1 in frequent domain. 1 as a step signal correspond to 1 over s in frequent domain. T correspond to 1 over s squared, and e to the minus a correspond to 1 over s plus a, and rest of it. Now, of course, remember, we are dealing with linear systems. So if I multiply that 1 by 5, then the Laplace transform will need to be multiplied by a factor of 5 as well. So that will become 5 over s. If I multiply t by 3, then the Laplace transform of that ramp signal will be 3 times 1 over s squared. If I multiply the exponential function by 6, then its Laplace transform would also need to be multiplied by 6. The principle of superimposition applies for linear system. If I multiply t by 1, Laplace transform of 1 is 1 over s, Laplace transform of t is 1 over s squared, then the Laplace transform of 1 plus t would be 1 over s plus 1 over s squared. So if you multiply signals in time domain, you can also multiply their Laplace transforms together. If you multiply one signal by a factor of constant, you can multiply their Laplace transform by the same constant. So its principle of superimposition applies for linear systems. So that will make our life a lot easier for more complex systems. For example, I have a function here in equation number 1. Ft equals to 3 plus 5 times e to the power of minus 2t. I need to find out the Laplace transform of that ft. Now I can reformat this into 3 times 1, that's the first term, 5 times e to the minus et in the bracket. 1, Laplace transform of 1 is 1 over s. Laplace transform of 2e to the power minus 2t is 1 over s plus 2. If I just go back one slide, e to the minus at, where a is 2, so it's 1 over s plus 2. And then you reorganize this becomes 3 over s, this becomes 5 over s plus 2, as shown in equation number 3. And of course, these are two terms that add together. I can find the common denominators and merge them together eventually. If I multiply this top bottom by s plus 2, I multiply this term by top bottom by s each. And I can find a common denominator, I add them together, I end up with the Laplace transform of 8s plus 6 over s times bracket s plus 2. That's the Laplace transform of this ft. So just to repeat, ft and fs represent the same signal. This varies with time, this changes with frequency. S is a complex frequency. We will talk about complex later on in my module, okay? Try another example. Inverse Laplace transform. This is going other way because, as I said earlier, for the same signal we can represent that in time domain, ft. We can also represent in frequency domain. Now, in the previous example here, I converted ft into fs. But of course, if I have sfs, I can convert that back to ft. That's called inverse Laplace transform. Okay, so over here I have an example here. I said fs equals to 2 over s plus 5 plus 4 over s plus 3. I want to find the inverse Laplace transform, i.e. the time domain representation of the same signal, Fs. Remember, Fs is the frequency domain representation, Ft is the time domain. So to do that, I'm going to reformat that into the forms I'm familiar with. So I'm going to take that 2 to the front. I'm going to take that 4 to the front. So it becomes 2 over 1 plus s plus minus 5, 4 times 1 over s plus 3. Now if I go back, remember these two. This is 1 over s plus 5. This is minus 5, sorry. This is 1 over s plus 3. If I go back to a couple of slides, I have s plus a. If that's 3, it becomes e to the minus 3. If this is minus 2, this becomes positive 2. Okay, so just go there. S over minus 5. This is minus 5, therefore it becomes e to the power of positive 5t. Negative to positive, positive, negative. This is 1 over s plus 3. 1 over, okay, top is 1. S plus 3, that's e to the power of minus 3t. Therefore, I get equation number 4. That's the inverse Laplace transform of this Fs. Now I'm doing that because we will need to use the concept of Laplace transform, inverse Laplace transform to solve our problems a lot. Okay? So we need to get familiar with the concept of converting from time domain Ft to Fs and backwards from Fs to Ft. So, and also it helps if you can memorize some of these pairs. Okay, impulse to 1. This left-hand side is time domain, right-hand side is frequency domain of the same signals. Okay, so remember this one, remember that one, and remember this one. That's all I'm asking you to remember. There's only 1, 2, 3, 4. Okay? All I'm asking you to memorize, put that in your head because it will come handy. It will be very, very useful. I'm giving you 2 examples here of how to find the Laplace transform from these tables. Okay? And also how to find inverse Laplace transform. You don't have to go back to all the mathematics of integration and all that kind of stuff. All you need to do is to rely on that table. Okay? And we will talk about some properties as well after this. But in the meantime, I'll give you a couple of slides or some questions to practice on. Okay? We will continue at next session. Thank you.